Good day. Yes, this is Lojas Daga. I'm presenting a concept note on my master's work. Yeah, so we're having a performance decline after quantization, pruning, knowledge distillation of deep learning models against decline in computational power in tiny machine learning applications. So tiny machine learning applications have different shortfalls when it comes to compression because models are normally trained in larger sizes, and then they are compressed down to sizes that can be optimized or can be suitable for smaller computation power. Yeah, this involves processes. This process involves quantization, which is better than compression, which we shall see in our methodology. And then it also involves pruning, which involves removal of or elimination of connections, or weights between neurons. The least important connections are eliminated from the neural network. Then the model is compressed, or it is shrinked, just like the terminology used. Then we also have knowledge distillation. These are the main keywords that we have in this publication or work. Now, there's also knowledge distillation of deep learning models, where we optimize, and the model is optimized to mainly use the highest weights or the highest values of weights, and then ignore the least weights for less computation, so that maybe we can optimize for high efficiency of our small tiny models on each devices. Yes, so let's get in. So this study investigates the trade-off between computational power and model performance in tiny machine learning applications, particularly in healthcare, as we shall see. The dataset we are using is a TB dataset, a sputum dataset that was collected in Uganda. Now we analyze the image. We analyze the impact of these compression techniques on model performance metrics, such as inference time, the time between the input and the output, the specificity, the precision. These are the metrics we can use rather than accuracy, because accuracy is not that reflective of the relationship when it comes to machine learning of late. Now, using the tuberculosis pattern slide dataset, propose a novel approach to model compression that aims to retain performance while reducing computational requirements. Yes, so we continue to the next slide. Problem statement. Now, the conventional machine learning models are trained and then optimized for tiny ML deployment. So yeah, and then often resulting in performance degradation. Now, this performance degradation is very pivotal, or it's very detrimental to models, because in healthcare, there's a certain limit of performance that is required when metrics are examined. There is a certain limit that is required in healthcare applications because of the diverse effects. It also goes on to applications like, let's say, transportation. A Tesla model would really require high performance because of what's at stake with the environment it performs in. Machine learning applications perform in environments that require delivery. Even, let's say, a Tesla car would require delivery in an environment whereby it doesn't have to make any error for self-driving cars. Yes, so metrics such as inference time, specificity precision are adversely affected by model compression techniques like quantization, pruning, and knowledge distillation. Now, the proposed solution to investigate the impact of model compression techniques on performance, I will propose using a tuberculosis pattern slide. Now, like you see here, sputum slides, like I said, the data sets. The data set will be annotated and analyzed to develop computer vision models capable of classifying Mycobacterium tuberculosis. Tuberculosis is very, when it comes to prevalence and incidence, it's very, very unpredictable. Just like um, let's say medical imaging with microscopes, which is PCB, clinical bacteriology, whereby we have to detect bacteria or this micro MTB in the sputum slides. So we need high performance, and yet working with compression. So how do we maintain performance even with compression? I mean, it's compression. That's what we're looking at. So the model will be compressed to various sizes using quantization, pruning, knowledge destination techniques, and deployed on different tiny ML devices. We want to look at different ML devices that we can use, different computation sizes, and then compare and see where can we probably work on. Then we can see which techniques can we use that out of this I wouldn't say cliche, but out of this usual compression methodology. What's out there? That's what we want to see. Proposed solution. The performance metrics will be evaluated against computational power to identify patterns and relationships in model behavior. Now, this behavior of the fall or the decline in performance is what we want to probably examine with decline in computational power across some different devices. Now, this goal is to propose a new approach to tiny machine learning model creation that retains all weights as in larger border sizes in order to acquire minimizing performance loss. Yes, because the system can't be um, we can't retain all the performance, but maybe we can even get more. You never know. So it's just a such question. Yes. So we go to the next slide, which is data sets used in the study across. The data set used in the study consists of 928 annotated tuberculosis sputum slide images. These were annotated with Pascal VOC format, whereby you have the image and the XML. You have the XML, just like we shall see in the ED of the dataset. So if we continue, the dataset was obtained from the Macquarie AI Lab website. This is an AI lab in Macquarie University. So this dataset was generated in 2016 and also published, a paper was published around it by a team of researchers, computer scientists, and other domains. So websites will be utilized. So this dataset will be utilized to train and evaluate the computer vision models. Now, the annotations will enable the model to detect and classify MTB accurately. Now, expected outcomes. The study aims to extract patterns and relationships in behavior of machine learning models on tiny machine learning devices, particularly in healthcare applications. Yes, so we're working with TB dataset, microscopy, slide images. So we want to see how we can maintain the performance of models on this data set, whereby we can still detect on edge devices. If you input an image, can we still detect that TB or the TB, MTB, or bacilli inside that sputum sample with high inference and other metrics, specificity and precision. So the expected outcome, by analyzing the impact of quantization, pruning, knowledge, distillation, and model performance. So we want to also analyze which techniques impact the most on the performance, which technique probably leads to the highest performance loss, and which technique leads to this performance loss. I don't know, that's for optimization. So we aim to harmonize variance between tiny ML compute power and model performance. Um, the expected outcome is a set of guidelines for optimizing tiny ML models in healthcare applications without significant performance degradation. Yes, so if we continue, we shall see the references there. Now, the first is a review, and then the second is this empowering healthcare, tiny ML for lung disease classification, which is pulmonary, just like TB. And then after, we shall see a group of team of CNN energy equals model for low power environments. So these are all tiny ML references, just like you see. We shall now shift to the data set. Just a minute. One break. Now we're going to so yeah. Okay, so now this is EDA on the data set we are talking about, which is the tuberculosis data set. It was acquired by a team from Macquarie University, Dania lab, from different domains. It involved microscopists who really work with the TB data sets or who work with the microscopes. It involved lab technicians who prepare these slides. It involved different stakeholders or different people, different domain experts. So, abstract. In this report, I present my exploratory data analysis on a TB sputum slide image dataset. The dataset contains Pascal VOC format annotations that have the XML. They have XML and image components, whereby the XML stores the annotation information, and then the image is what is probably going to be mapped. Yeah, so the goal is to understand bacilli distribution characteristics across images, guiding future diagnostic improvements. Now, tuberculosis remains one of the leading infectious diseases globally. Like you see here, tuberculosis remains one of the leading infectious diseases globally. This EDM analyze the data sets composition. Tuberculosis, I think, it has a latent TB and then active TB. So I think most of the population in the world, let's say 1 billion, okay, not most, but a significant amount, let's say 1 billion, have latent TB, which is inactive. It hasn't been activated due to probably weak, probably bacterium or very low bacterial load. But then when the immunity is suppressed, it turns into active TB, whereby the bacilli starts to thrive inside the system. It can go from even just the pulmonary system into the what? Into the other body parts when you have a very low immunity, let's say for HIV. Yeah, so this EDM aims to analyze the data set composition, bounding box distributions, and the spatial patterns of TB bacilli within microscopic images. Our image here, it shows a sputum slide, and then it is magnified to 100, or let's say 1000. Yeah, this is 1000. Yeah, when it's magnified to 1000 times 1000 magnification, we get to have a clear view of the different artifacts and components of the sputum sample. So then we get to annotate the different bits of the what? Of the bacilli. So as we see the annotations here, the sizes of the bounding boxes, the width and the height, we are going to see some visualizations down there to probably bring this out, the sample of the data set. Yes, so that is the description. The dataset consists of annotated TB sputum slides in Pascal VOC format. Now, the Pascal VOC format divides the annotated dataset into image and XML files. So here, what we're seeing on the right is the annotation. There's the annotation information. So as you see here, annotation source database is stored in the Macquarie Automated Lab Diagnostics, Macquarie Lab. Then the annotation is Macquarie University, where the happened. Then the source was Mulago National Referral Hospital, which is also in Kampala. Segmentation segmented is 0. Now here we're seeing the bacilli, the label TB bacillus. So that's the label in case we get any detection in these detections. Yeah, so this is a TB bacillus, TB bacillus, TB bacillus. When it comes to the detection, it will show TB bacillus detected. Then we can do maybe a count, and then we can have something quantifiable. Yeah, so if we continue, the XML file holds the annotation details. Each image contains multiple bounding boxes labeled as TB bacillus with coordinates indicating the location of the bacillus. Yeah, in the what? In the sample, which is, I don't know, it maybe close the closer the I don't know, we can maybe get some insights from how close the bacillus are close to each other, but that's probably further study. So the TB images were made from fresh sputum stained using Ziel-Nelson stain to bring out the for visualization. Yeah, or for microscopy. Normally, Ziel-Nelson is used. The TB probably sterilized with a fixing. I think it's an acid first, and then after they're stained with Ziel for visualization, it brings out the bacillus and also the different cells. Now, these were examined under at times 100 or 1,000 times 1,000 magnification. So this is maybe 1. So when you magnify it by 1,000 times 1,000, you get this. And this is when you can easily do our what? Our bounding boxes and maybe train a model to observe the bacillus in the slide. Now, methodology, the analysis includes object count per image, bounding box dimensions, aspect ratios, and spatial distribution itself, assess bacilli frequency, size variation, and clustering tendencies. So here, as we see, we are seeing the distribution of bacilli per image. So how many bacilli we have per image? Now you can see we had a sample of our data set and it has frequency of 1 across 5, between 5 and number of bacilli. So 5 to, for this image, it had between 5 to that. And then here, the image had between 8 and 6 and 9. And then here we had 10. So here we are seeing a plot of width of bounding box size, like I talked about, the width and the height of the bounding boxes. That can also be used in further feature extraction, whereby we can compute maybe the middle point from that bounding box and continue to see what we can extract. Maybe the shape of the bacillus, maybe the type of the bacillus, maybe the family of the bacillus, maybe if it's latent, or maybe if it's an earlier stage. Yeah, so different things. So there, then we have the width and the height. The legend. So if we continue, now key observations, bacillus count vary across images, indicating the different bacteria loads. Now, Yeah, so different bacterial loads among different samples. And then bounding boxes sizes are small, reflecting the microscopic nature of TB bacilli. Then the aspect ratios suggest that bacilli appear elongated but sometimes square. Spatial, so it's more of rectangular bounding boxes. Now, the spatial distribution shows widespread presence across images. Conclusion and future work. Yeah. So the EDA verified dataset integrity and provided insights into the bacilli distribution. Yes, yeah. So we picked insights and we verified dataset integrity. Then future work may involve expanding the data, improving bounding box normalization, and applying object detection models for automated analysis. Minus that, I want to introduce the team. So we have Dr. John Quinn, Dr. Rosna Kasi, Mr. Pius Mugaga, Madam Bianyima, David Lubega, and Alfred Andama, who's also a doctor right now, microscopist. These are the experts who worked on the data set. And the paper is called The Convolution Neural Networks, Microscopy-Based Point of Care Diagnosis. Proceedings, yeah, it was then submitted to this conference. Yeah, then also we have the WHO reports and also the Pascal VOC challenge where we had to normalize and understand the Pascal VOC format. Once the data set was created. But minus that, I think the key takeaways are to see insights and also see a relationship between um, model compression and performance declination. But minus that, I beg to submit. I'm Bamunda Galesius, a computer science student, and this is my work for my master's. Thank you.